It's a pleasure to have Professor Von Oppen with us today, who is the first speaker of this session. He has deep interest in low-dimensional quantum system, particularly from the perspective of quantum transport. In recent times, he has been intensely involved in realization of Majorana fermions in the context of condensed matter physics, and his work has motivated many experiments. It is also, I think, in some sense, Majorana fermions are closely related to the theme of the school, because they find their hope to be the future of quantum information processing and quantum information communication through topologically protected qubits, which are intensely related to Majorana fermions. But as far as today's topic is concerned, he will be talking about Hilbert space geometry of random matrix eigenstate. So I don't know if it will be connected to Majorana fermions, but that's what he's going to talk about. Felix, the stage is yours.
Okay, thanks for the nice introduction, and let me actually also start by thanking the organizers, in particular Pragya, for inviting me to give this talk. So there will be no Majoranas in this talk. I also didn't yet notice a very deep connection to Majoranas. From what I understand, this session is supposed to be about entanglement and random matrix theory. So it turns out that in this talk, there will be a lot of random matrix theory, but there will also be a little bit of a connection to entanglement, but it's going to be in passing in many ways. So this work that I'll talk about is recent work that I did together with a very good master student, Alexander Penna. It got started in discussions with Gergely Zarand, who's in Budapest. And then for some of the technical things, it was very helpful to get Martin Zirnbauer on board, who is one of the is the world expert perhaps on using supersymmetry techniques in the context of random matrix theory. Okay, so this work actually got started when I read papers that Pragya Shukla was writing together with Michael Berry. And the problem that they discussed was the following. They looked at random matrix ensembles as a function of parameters, and then they asked whether the eigenstates as a function of these parameters have they will have a Berry curvature, and the question was, what is the distribution function of that Berry curvature? And what they did was to compute these distribution functions based on small random matrices, 2 by 2 or 3 by 3, and then they were quite inventive in how to use these results for small random matrices to deduce results for large random matrices, which are really the sort of random matrices that would describe generic quantum systems. And so here you see, maybe I should get a pointer. Yes, here it is. Okay. It still doesn't, that was not good. Let me so here, there we go. So here are some of their results for that distribution function. And the red curves are their prediction. The analytical equation is underneath. And the histograms are numerical results for larger random matrices, and they actually work quite well. I got into this. Yeah.
Your slides are not.
Say it again.
Your slides are not moving. Are you moving? Your slides are not changing. Oh,
no,
yes.
Okay. You okay? There should be your paper on it so far. Anyway, so I got into this because I thought I know how to compute this exactly for large random matrices. And so we did the calculation, and then we were actually disappointed. And when just a few days before we were about to submit to the archive, we found out that someone had already done that calculation more than 20 years ago. And it turns out that Ben Simons from Cambridge, together with a student, had worked out that distribution function exactly for large random matrices at that time. And here is the result for the Fourier transform or the characteristic function of that distribution function. And it obviously then it agrees very well with numerics. But then, okay, it turns out that Pragya, together with Michael Berry, actually went on and they studied then in a different quantity that goes beyond the Berry curvature. And that was the quantum metric tensor of these random matrix ensembles. And so we then also thought, and they again did it approximately, and we then went ahead and calculated that exactly. And that's the main topic then of this talk. And our result, in some senses, is can be said in one slide. It's a very simple function, still complicated looking, but basically the Fourier transform of that distribution function is or the characteristic function of that exact joint probability distribution for the quantum geometric tensor, and we did it for the Gaussian unitary ensemble, has a simple, relatively simple form. It's some exponential factor and a rational prefactor, and the rational prefactor has this form. Now you may say that, okay, fine, that's what it is. But let me try to walk you through this over the course of the next hour, starting by explaining to you what exactly is this quantum geometric tensor, then introducing or reminding you a bit about what random matrix theory is about, and then discuss this result. And even though this looks kind of horrible and intransparent and just whatever it is, let me try to convince you that there are some things here that one can actually understand and that have interesting connections to other things that are interesting at the sort of at the qualitative level, or that one without having to go into any technical details. And if then there's any time left at the very end, I would also give you a few hints of how to actually derive this. That's a supersymmetry calculation, but I may run out of time before we get there. Okay, just so you believe that what
just a quick question, clarification.
Yes, sorry.
In the first plot which you showed, there was only one parameter as a function of which you, I think in Berry's paper and Pragya's paper, just one parameter. Is the parameter space one-dimensional, where you are saying this curvature, it's two-dimensional? When for non-trivial Berry phase, I need two-dimensional probably. If I need anything different than 0 and pi.
Yes.
So
and this is also this is actually was even three-dimensional, and what's actually plotted here. Yeah, what's plotted here, I wasn't so. It's actually the trace of this quantum metric tensor.
Oh, I see. Okay. Thank you.
So it's actually it's the sum of the diagonal elements of the tensor, and the Berry curvature is actually the off-diagonal one. But I'll get there and go through it more slowly.
Okay. Thank you.
Okay, and this is just to convince you from the start that these exact results actually work. So the left plot here is again the trace of this quantum geometric tensor, actually now for two parameters, and the orange dots are this equation, and the blue curve is the numerical histogram, and it just works perfectly. And the same goes for the off-diagonal elements of this quantum geometric tensor. Okay, so then let me start by introducing what this quantum geometric tensor actually is. So imagine that you have a family of Hamiltonians that depends on some parameters. And I'll denote these parameters by lambda. This is a vector. There's a set of parameters, and you can think of them as being either magnetic field or electric field or the shape of a quantum dot or any other parameter that would affect the Hamiltonian of the system. If we are then discussing looking at the spectrum of that Hamiltonian, then there will be eigenstates and the corresponding eigenenergies, and of course both the states and the energies will depend on these parameters. So in speaking somewhat pictorially, we can think of these sets of eigenstates as sort of manifolds that have some shape, and you can then be interested in defining distances on that manifold and in curvatures of that manifold. Now, for those of you who are mathematically inclined, there is actually no manifold here. These are complex line bundles that we are talking about, but I guess that's a detail that is not so important, and I will certainly not be at that level of mathematical sophistication because I'm simply not. Okay, so we have these manifolds, and now we would like to discuss distances and curvatures. Now, one thing in doing so that you need to remember is that these quantum eigenstates are really rays in Hilbert space. If we multiply these quantum eigenstates by a phase factor, then we're still talking about the exact same state. And of course, we can choose this phase factor differently for different values of lambda. And so whatever distance measure we are defining on this manifold, we should make sure that the distance measure does not depend or does not change under these gauge transformations of these eigenstates. If we multiply these eigenstates by a phase factor, the distance measure should not be changing. And it turns out that there is such a measure, and that measure is called the Fubini-Studi metric. And so if you now want to look at the distance between two eigenstates that are for infinitesimally different parameters, so at lambda and lambda plus d lambda, then one would define the square of the infinitesimal distance as 1 minus the overlap of these eigenvalues, eigenvectors squared. So basically what this measures is how fast these eigenvectors are going away from being parallel as you're changing the parameters. And it's also clear from this definition immediately that this kind of distance measure will be insensitive to these gauge transformations because it's an absolute value squared. So if you just change phase factors here, that's not going to do anything to it. We can then expand this out to quadratic order in d lambdas, and that then defines the corresponding metric tensor. And that metric tensor then is what people call the quantum metric tensor, and you can actually, and it's the real part of a tensor, and this tensor then you can write explicitly like this. It's given by overlaps of the eigenstates with some derivatives with respect to the parameters. And actually, it turns out that the imaginary part of this tensor also has a important meaning. And then the combination of the quantum metric tensor, which is the real part, and the imaginary part is known as quantum geometric tensor. And that's the quantity that I want to discuss. This quantum geometric tensor has several important properties. It's invariant under these gauge transformations, multiplying these eigenstates by a lambda-dependent phase factor, as we already saw. It's Hermitian, and as I said, the metric is governed by the real and symmetric part, and that's known as quantum metric tensor. And then the imaginary part, which is also anti-symmetric, that is actually the Berry curvature. So the quantum geometric tensor, which is the whole thing, describes both the metric of this manifold and the curvature of that manifold. So we have all these quantities combined into one tensor. And the full distribution function of that tensor is the main topic of this talk. Okay, so then, of course, it's an important question, why is this actually interesting? And the first answer to this is that there are many families of Hamiltonians with non-degenerate spectra that one may be interested in. And so in particular, for example, this happens if you have some, say, condensed matter system and you're interested in its phase diagram at temperature equal to 0. So you're varying some parameters. I don't know, think of the quantumizing model. And you vary some parameters and the system can exhibit different phases. So then this quantum geometric tensor is an interesting quantity to characterize the system and to characterize these quantum phase transitions. Another case that, or connection to condensed matter physics is if you look at bands of Bloch electrons, then in many ways you can think of the wave vector as being the Bloch vector as being a set of parameters. And so that's another context in which this quantum geometric tensor is quite important. And we know by now, of course, that the quantum geometry, both the curvature locally and globally, the Chern numbers are determining the behavior of electrons in very important ways, for example, in the context of the quantum Hall effect and the anomalous Hall effect, both quantized and unquantized. You could also think of Fermi liquid quasiparticles that basically as being such a parameter-dependent family of Hamiltonians, and here the parameter would be the position or the location on the Fermi surface. So there are many contexts in condensed matter theory or condensed matter physics where you have such parameter-dependent families of Hamiltonians. More physically, this quantum metric tensor governs the physics of quantum quenches if you have small changes of parameters. So imagine you change the parameter slightly from lambda to lambda plus d lambda, and you ask the question, how likely is it that the system remains in the same eigenstate manifold after you've changed the parameter by d lambda? Well, the answer to that question is precisely this distance measurement. So if you want to discuss quantum quenches with small changes of parameters, then their properties are well described by this metric tensor. Another context is, I already mentioned, quantum phase transitions. So what happens at these quantum phase transitions typically is that the energy level, the spectrum of the system becomes gapless at the transition and is gapped on both sides of the transition. And one way of writing this quantum geometric tensor is by, in terms of the eigenvalues of the unperturbed Hamiltonian and the eigenvectors of the unperturbed Hamiltonian, and then having matrix elements of the derivative of the Hamiltonian with respect to the parameters. And what you see is that if eigenvalues, if you go to a quantum phase transition, then there are contributions where you have the energy differences go to 0. And so you expect that this quantum metric tensor actually becomes singular at quantum critical points. And you can characterize these quantum critical points by the behavior of this quantum geometric tensor. And that's something that was done in this paper quite a while ago. Another interest is in if you look at the adiabatic approximation, and this is something that was pointed out by Michael Berry already quite a few years back. So imagine that, for example, the easiest example would be a molecule where you have slow nuclei and you have fast electrons. And so there would be a Hamiltonian of the electrons, of the fast variables, that depends on the nuclear coordinates, because they determine the potential that the electrons are seeing. But of course, the nuclei themselves can also move, and so there is some kinetic energy term for these nuclei. And in the Born-Oppenheimer approximation, you would make the start from the fact that you factorize the eigenstates. You have the electronic eigenstates, and you have the eigenstates of the slow variables of the nuclei. And you can then discuss deviations from the strictly static assumption of strictly static nuclei. You know that if you take the nuclei around in a circle, then you would the electronic degrees of freedom, the electronic wave function would get a Berry phase. But conversely, also the fast degrees of freedom are acting back on the slow degrees of freedom and exerting forces on the slow degree of freedom. And it turns out that the effective Hamiltonian for these slow degrees of freedom involves precisely this quantum geometric tensor. So the Berry curvature enters into the kinetic term of or kinetic energy of the slow degrees of freedom in the form of the corresponding Berry vector potential or Berry connection. So the curl of this A is just the Berry curvature that is the imaginary part of the quantum geometric tensor. But it turns out that in addition to this sort of magnetic field that is acting on the slow degree of freedom, there's also an electric potential that is acting on the slow degrees of freedom. And that electric potential is actually given precisely in terms of the quantum metric tensor. Q alpha beta is symmetric, so it's only the symmetric part here that contributes. So it's only the quantum metric tensor. So you see that the dynamics of the slow degree of freedom is precisely, or the corrections to the adiabatic approximation are governed precisely by this quantum geometry, both the Berry curvature and the quantum metric tensor. And in fact, one application of this is to the semi-classical dynamics of Bloch electrons, where, as we discussed, K is the parameter. And so that's a standard approximation and kind of old-fashioned solid state physics. But now the Berry curvature, for example, adds additional terms in these semi-classical equations that basically correspond to a magnetic field in K space that exists in addition to possible magnetic fields in real space. So the Berry curvature here acts as a magnetic field in K space, and that, of course, is what's behind the anomalous Hall effect, both again quantized and unquantized. Okay, so I hope with that I convinced you that this quantum geometric tensor is actually an interesting quantity to study. Let me then briefly...
Felix, can I make a comment here? Just an addition, just a comment and a question. So the comment is, I think even for, if you have non-eigenstate and they evolve under a static Hamiltonian, the energy fluctuation of the state is also exactly equal to the geometric tensor, right? If you calculate the standard deviation of energy, of course, the expectation value is 0. Right. Because it's a static Hamiltonian. But if you look at the standard deviation of energy, that's also governed by this, which is also like related to the velocity of evolution in the parameter space for the state.
Right. Yeah.
And that's another interesting. Okay. So the other question is, are there any topological invariants which you can define through the, like with Berry phase, we do define topological invariants. Now with the G mu nu, do we define like Ricci scalars and so on, which can act as a topological invariant, which are becoming ill-defined at the transition? Is this a possibility, or that's
sounds like a very interesting question. I don't have, I don't know. Of course, so with the Berry curvature, then you can define trend numbers and so on. Whether there's anything topological about the metric.
Because I can define Ricci scalars, right? It has two indices. I can contract it fully and then define different scalars, which are probably coordinate invariant. And then the question would be, those scalars are interesting object or not topologically. And
we can discuss at some point. I simply don't know.
Okay. Thank you. Thank you.
Okay. Good. So then let me just also introduce briefly random matrix theory, although maybe it's unnecessary in this context, but it may still be fun for the anyway. So it turns out that random matrix theory comes from nuclear physics, and in fact, it kind of goes back to this toy model of a compound nucleus scattering that was supposedly standing on Niels Bohr's desk in Copenhagen. So the idea is the question is basically what happens if you shoot a nucleon, say a neutron, at a nucleus, and so here this is the nucleus with with whatever number of protons and neutrons that you have, and if you shoot this neutron at sufficiently high energy, then of course it will start to produce some sort of rather chaotic motion within this billiard. And that then got Wigner later to think of the fact that, look, I mean, that this motion is chaotic, and the details of the interaction and the details of the Hamiltonian shouldn't be so important because of this chaotic motion. So let's just replace the Hamiltonian of the nucleus by a random matrix, and let's just assume that all the matrix elements are Gaussian distributed, and let's also impose that all bases in which we can write this Hamiltonian are equivalent with respect to one another, or equally likely, and so that you can arrange by making the distribution function dependent on the trace of the Hamiltonian squared. That makes it Gaussian, and it's also independent of which. Because of the trace, it's independent in which of the basis that you're using to describe the Hamiltonian. And it actually turned out that that was very successful. So here are some data from the nuclear data ensemble that just one of the resonances that you observe in some of these compound nucleus reactions, and there are many of them, and they have been analyzed. And then what people looked at was the spacing between neighboring levels. And they made a histogram, which is this curve. And Wigner, based on 2x2 matrices, was computing the corresponding probability distribution for this random matrix assumption. And the agreement is very nice. And it certainly, the prediction of this random matrix assumption is very different from what you get if you assume that the eigenenergies are uncorrelated with each other. That's the Poisson case. And there you see that this spacing distribution, so that's the spacing and that's the probability of that spacing. The spacing distribution looks very different, and in particular, small spacings are very likely in the Poisson case, but they're very unlikely in the random matrix case. Now, in the meantime, that has been that kind of behavior has been found in many different contexts. You can do that for quantum chaos, so small billiard problems like the Sinai billiard here. You can do it for lattice QCD. You can do it for atomic physics, say hydrogen in a strong magnetic field. You can do it for correlated electron systems. These are kind of Hubbard-like models. And if they're integrable, they show Poisson statistics. And if they're non-integrable, then they show random matrix statistics. And most recently, this has played an important role in the context of many-body localization. So this random matrix theory has pervaded basically all branches of physics by now, and is an interesting starting point to discuss chaotic or disordered systems. So one thing that is kind of remarkable is that there are very, very few exact distributions known for random matrix theory. So there, basically, I'm mostly aware of two cases in which there are simple distributions. One is the Porter-Thomas distribution. So that's the probability distribution for the strength, this absolute value squared of the eigenfunctions at a certain position, or of an element of the eigenvectors. And it turns out that they are basically exponentially distributed. This is known as Porter-Thomas distribution, and that's the one place where this connects with entanglement, because this Porter-Thomas distribution played a central role in the claim by the Google quantum computing people that they've realized quantum supremacy in their superconducting processor. So there, this Porter-Thomas distribution was an important element of that argument. Another case where there is a simple distribution is one that is close to my heart. It turns, if you look at the level curvature, so the second derivatives of the levels with respect to a parameter, then it turns out that their random matrix distributions are very simple. They're just Lorentzians to some power. And that was first observed numerically by Dlazhevsky and Delant. And then after that, I managed to prove that that is really the exact distribution for the conventional Dyson ensembles. And actually, it's that calculation that actually has a lot of similarities to what I talk about today. And in that sense, this has kind of been a nostalgic project because but that also why I got involved in this, because I thought I knew how to compute these distributions exactly. Okay, so then let's get back to the quantum geometric tensor and combine that with random matrix theory. So the basic setting then is to look at a Hamiltonian that is a parameter of is a function of two parameters, x and y. And we assume that H0, Hx, and Hy are all Gaussian taken from the Gaussian unitary ensemble, where the Gaussian unitary ensemble is this just a general Hermitian matrix with that Gaussian distribution that I mentioned earlier. But we do not impose any other symmetries or anti-symmetries for our random matrices. They're just arbitrary Hermitian matrices. And again, we choose H0, Hx, and Hy independently from independent GUE distributions, although the averages over Hx and Hy are actually optional. You don't need them to get the result. You can in principle simplify that. So then the probability distribution is given here. It's again just e to the minus trace h squared for all of these three matrices. And so what we want to average are this quantum geometric tensor. And you remember that we had this perturbative, this expression exploiting perturbation theory. And it basically involves matrix elements of the perturbation in the numerator and energy differences in the denominator. And it's a 2x2 matrix because we have two parameters, and those are conveniently written in terms of a unit matrix contribution and the contributions that involve the three Pauli matrices. And then we want to compute the probability distribution for these G0 and the three elements of this vector G, insisting, so that's these two delta functions, and then we insist that we take a level at the center of the spectrum, and we average over all these three Hamiltonians. That's the mathematical task that you have. Now, again, I'm not going to go into details here, but instead, let me try to convince you why, this looks just terrible, but let me try to convince you why there is a chance to make some progress and why this is kind of interesting. So, and that starts from this expression. And perhaps the best thing to do is to first look not at the random matrix case, but to first look at the integrable case. And it turns out that in integrable systems, these eigenvalues, the eigenenergies, are statistically independent of one another. They don't know much about each other. And so if you then look at this expression, these are just some matrix elements. You can kind of ignore them to start with. All the action is in the denominator. And if these energies don't know anything about each other, it's quite likely that they become close to zero. And if they get close to zero, then the contribution to the sum becomes large. but even before that, the different terms in the sum are statistically independent of each other. Then they don't know anything about each other. And that reminds you of a random walk. So it's a sum of statistically independent terms that defines the random walk. And then that reminds you of the central limit theorem. So in principle, then you would think that a large number of random variables, or the sum of a large number of random variables, should be Gaussian distributed. And so maybe, this G should have a Gaussian distribution, but it doesn't. And the reason is that there is an important condition in the central limit theorem that the average and the variance of these individual terms have to exist. And it turns out that that's not the case here, because the individual terms have an extremely broad distribution. And in fact, you can easily work it out if you assume that the E's are statistically independent. So for integrable systems, then these individual terms behave like 1 over the spacing squared. The spacings have a finite probability to become 0, and that means that asymptotically at large x, the distribution of these x's falls off as 1 over x to the 3/2. And so the individual steps have a distribution that falls off as 1 over x to the 3/2. And it's clear that this doesn't have an average and it doesn't have a variance. If I try to calculate the average, the average of x, it's going to diverge. And if I try to compute the variance, it definitely diverges even worse. So this is not leading to a Gaussian distribution. And you can actually just simulate this and compute it, look at a sort of ordinary random walk, and then you look at a random walk with this kind of distributions of the individual steps, and you see that they look just dramatically different. These involve both of these figures involve 10,000 steps. And what you see here on the right side is that the behavior here is governed by completely governed by individual steps. There are a few steps that are huge, and most of the time nothing at all is happening on that scale. And so this is known as a Levy flight. So these distributions of this quantum geometric tensor are closely related to Levy flights. And of course, for these Levy flights, also these stable distributions are known, and analogous to the Gaussian distributions that you get for Brownian motion. And you can just look it up in the mathematical literature. And so for integrable systems, we can get the answer on the spot by just looking in books. And the answers are typically given in terms of the characteristic functions. Again, that's the Fourier transform of the distribution. And there are two cases here. If you have a diagonal element of the quantum geometric tensor, then this numerator is an absolute value squared. And so this is a sum of positive terms. And then this is the distribution you get, and the relevant one here is the red one. That's then the distribution as a function of G. And if you look at off-diagonal elements, then of course the numerators here have random signs, and then it turns out that the stable distribution, or the characteristic function of the stable distribution, is given by this expression. So the only thing here to remember is A, they exist, and B, you have this e to the minus square root of psi. Psi is the Fourier variable that is conjugate to G. Okay, just remember that. And then there is this. Here's again just this distribution. Okay. So for integrable systems, we can just look it up in the literature. And so what makes these calculations possible is actually that it's in some sense that it's so complicated that it's a sum of many terms, and that as usual in statistics, leads to simple distributions. Okay, so then you can still discuss this a little bit further. So this is the diagonal case. This is the off-diagonal case. It turns out that in the diagonal case, you can actually do the Fourier transform and compute the actual distribution function. And you see that there is a singularity, that it behaves like 1 over G to the 3/2 at the small g. And that actually turns out is related to the fact that the leading singularity of this characteristic function goes like square root of psi. So those two things are directly related. You also see that the full distribution is also decaying like 1/3 g to the 3/2, just as the individual step. And this means that the sums are essentially dominated by a single term, which is a generic feature of these Levy flights. And then in the diagonal term, you also see that the distribution function goes to 0 at small g faster than any power, because it goes like e to the minus 1/t. And that's another interesting fact about the distribution. Okay, so now random matrix theory. One thing that we already saw from random matrix theory was that these energy denominators now, there's level repulsion, and so they are suppressed. And what you then expect is that that the distribution of the g's should be decaying faster at large g. And in fact, Pragya and Michael Berry were predicting that it should decay as g to the minus 5/2. What we see is that in the random matrix case, these g's are really distributions of these are Levy flights with correlations, and it's not really uncorrelated sums, but it's correlated sums. And yet, it turns out that we can compute this distribution function exactly. There seems to be some noise in the background. Okay, anyway, so let's go on. So again, so this is the result. And let me just point out some things. So first of all, it turns out that at small psi, in this case, if you specify this general result that I gave before to the diagonal or off-diagonal matrix elements, then you find that the leading singularity now is no longer square root of psi, but psi to the 3/2. And if you then look at what that means for the distribution functions, they indeed decay as g to the minus 5/2, as Pragya and Michael Berry found or argued on the basis of small random matrices. You also notice that this exponential factor, I asked you to remember this e to the minus square root of psi from the Levy flights. And you see that this x is also just square root of psi. You recover these e to the minus square root of psi factors again in the random matrix distribution. And so they look just like for the integrable systems. And so all the random matrix correlations are then, and the level repulsion are contained in this rational prefactor. That's what's accounting for the level repulsion or the correlations that are that exist in the random matrix spectra. Okay, so that's basically most of what one can say. Then there's a few things that one can extend this to, so we can compare this. We can look at the distribution of the trace of this quantum geometric tensor. This is also something that Pragya and Michael Berry were doing. And it turns out that for a single parameter, this is the result. And that was actually previously discussed in this paper using a totally different method. And for two parameters, this is what we find. And for more than two parameters, we can only do the asymptotics. But what you generically find is that at small g, things decay faster than any power. The powers seem to be slightly different from what Pragya and Michael Berry get from their approximate calculations. And at large g, they always fall off as 1/g to the 5/2, as we already argued. Okay, so you can also look at this in a slightly different way. So this quantum geometric tensor, the distribution function really depends only on the eigenvalues of the quantum geometric tensor. And so then we can write distribution functions as a function of the two eigenvalues. And that's what's shown here, both what we computed and what you get if you do it numerically by diagonalizing random matrices. And believe me, and it's clearly seen here that the two are just in perfect agreement. You can also ask whether this has anything to do with reality. And so what we did was to look at a random flux model, an Anderson model, basically with random fluxes. And we computed this quantum geometric tensor for different disorder realizations. So Tij and the epsilon j's are chosen random in some appropriate way. And we, as the parameters, we're putting the system on a torus, and as parameters, we look at the phases, the fluxes that you can put through the holes of the torus. And sure enough, if you compute the quantum geometric tensor or distribution function for that, then that agrees well with the prediction. So these are 3D, it's a 3D random flux model. And this is for the trace of the quantum geometric tensor, or rather it's a diagonal element simply. And this is for the real part of the off-diagonal element, and the full lines are the theory, and the points are the simulations. So that works also very nicely. This is actually something that got us into the project initially, because we also had done this previously for at the Anderson transition. And there you get slightly different distributions. So these are at the critical point. The data on the previous slide were in the metallic phase of the Anderson model. Okay, so finally, I think I should get to an end. So I can still spend 2 minutes on the derivation, but I will basically skip it. So we already said that this is what you need to compute. And so the trick is to first do the averages over these. So the first trick is to go to the characteristic function. And then these g's appear in the exponent, and these h's then averages over these matrix elements over the perturbations become just Gaussian integrals, and you can just do them. And you get some expression that involves products of many differences of many eigenvalues. And that you're supposed to average over the random matrix ensemble. And the trick here is that you can use the joint eigenvalue distribution of this random matrix ensemble. And then you see that it involves the same product of differences of energies, and you can then rewrite this as an average over a determinant or over determinants of a random matrix that is one dimension smaller than the original random matrix. And then you just have an average of a bunch of determinants. And this trick comes from these old papers of mine. So people in the meantime have been looking at these spectral determinant averages in more detail. And you can also just straightforwardly calculate them by, it's very, very tedious, but it's straightforward to calculate them by supersymmetry. So the idea here is to exponentiate these determinants using fermionic Grassmann variables for the numerator and bosonic variables for the denominator. And then there's a machinery, what to do in the limit of n to infinity, which involves Hubbard-Sartanovich. And if you like, and if you're Martin Zimbauer, you use superbosonization, but it also works in different ways. And you get some integrals over some, ultimately over some complicated coset spaces. But it's well known how to do this. And in this case, it's nice because the result is actually semi-classically exact. So you just need to do Gaussian integrals, get some expression, and you need to, in the end, sum over many symmetry-related saddle points that generates this rational function. And each one of these terms in the sum is divergent, but the sum becomes a nice 0 divided by 0, from which you can extract the actual result by taking the proper limit. Okay, so that's the result. I don't think it's terribly interesting to go through the technical details, but I hope that I convinced you that this quantum geometric tensor is an interesting quantity, B, that the random matrix result for it is relevant for actual physical quantities, such as the what we were discussing in the context of the this random flux model or this Anderson type model. Maybe I should say that the elements of the quantum geometric tensor there are closely related to the conductance, Hall conductance and longitudinal conductance, and one can use them in scaling theories for the Anderson transition. Finally, I hope that I convince you that despite the fact that this is a horrible expression, there are some things here that one can understand, and in particular, one can understand why it is that this complicated quantity, one can find an exact distribution for this complicated quantity, and that there are interesting relations with Levy flights of this result. Okay, with that, I'm done, and I thank you for your attention, and I'm happy to answer questions.
Okay, thank you, Felix, for the wonderful talk. It was very illuminating. So now the floor is open for questions. If you have any questions, please unmute yourself and ask. Can you hear me? Am I audible?
I hear you.
Okay, fine. Sometimes you just don't know if you're connected or not. Any question? Pragya, is it you? I mean, the voice is somehow breaking. Hello?
Yeah. Somebody is muting me again and again.
Oh, God.
I don't know, on your end. Yeah. Anyway, so now I am unmuted. Felix, very nice talk. I wanted to know, like, whether you considered the generalization like this h is equal to h naught plus hx plus hy is an approximation. Usually, like, you have to consider the derivatives of the perturbed Hamiltonian. So, like, can you expand your formulation to that kind of more realistic situations? That was my first question. Second thing is, have you considered the many body, for example, you consider? Yeah.
I didn't quite understand the first question yet. What do you want to do different? What's more?
H is equal to h naught plus hx plus hy. Is hx plus hy are perturbations of h naught, right?
Yes.
But in general, you have to consider that there is h naught and it is perturbed by 2-parameter perturbation. So you need not write that as hx plus hy. It need not be just addition, right?
Right.
Any kind of perturbation, you consider the metric or the curvature for any kind of 2-parametric perturbation, right? This is a linear approximation, this h naught plus hx plus hy.
Right. So that maybe we can do the other question. So, but I mean, in some sense, I'm only interested in the derivatives at x equal to 0 and y equal to 0.
Exactly.
Right?
Yeah.
So as far as that is concerned, I think that assumption seems to be okay to me. The one thing that we do assume is that the hx and hy have the same variances, so that they're the same kind of perturbations. I think that one can go beyond that, but it becomes very. And I think we have some results on that in the supplementary material. But it's becoming awkward relatively quickly. So you should, in principle, rescale your parameters.
Yeah. Actually, the thing is, you talked about random flux model and you talked about the nearest neighbor hopping. And in nearest neighbor hopping, like the thing is, like using GOE or GUE rather,
Yeah.
I mean, it's not very obvious, right? That you can use GUE.
The parameters were the fluxes through the torus.
Oh, okay.
So
okay.
the analog of X and Y are the fluxes through the two openings of the torus, or two of the. Actually, okay. It was three. It was actually three in that case. It was, but never mind. So since it was a 3D system,
so have you tried to? Yeah.
And so of course with the
so have you
have to be careful. You have to be careful that you're in the in the metallic phase, so that random matrix theory is applicable. You're not allowed to go too close to the Anderson transition, and certainly not to the other side of the Anderson transition. Yeah.
Yeah, so I had some results in that connection, like when you have a more general, you are away from GUE regime. Anyway, but what I was going to ask you was, have you thought of like doing the calculations for at least 2 electron system, like where you have interaction, not only like random flux model, like you also have interaction, two electron system?
No, we haven't.
Why I'm saying that, like, see, the thing is, this whole thing is dominated by a 2 by 2. Why you with all your calculations you still get as we predicted? It's just because what Fritz Hake and many people had said long time ago, that in all these calculations, what matters is the nearest neighbor interaction, because ultimately you are having the nearest neighbor, the curvature or metric is dominated by, because E1 minus E2 is coming in the denominator, and that's why it is dominated. So basically what is ultimately it becomes, the effective model is 2 by 2, you know.
So I think that I partially agree with what you're saying. So I completely agree that the asymptotics of this distribution for large G, those are just 2 by 2 matrices. That's near degeneracies in the spectrum. But the rest of the distribution, the bulk of the distribution, is not the 2 by 2 matrix. There, the n by n actually does matter. And you may or may not be interested. Because, you may not be interested in the result, but the bulk of the distribution is different. And for example, the behavior at small g, e to the minus 1 over g with some power law prefactor. This power law prefactor, for example, is that comes out of the exact distribution, is different from what you have in your paper. So the one e to the minus 1 over g is correct, but the prefactor is different. So the bulk of the distribution does know about the fact that it's a large random matrix. For the asymptotics at large g, no argument whatsoever. That's of course just two-level systems ultimately, and there's. I would have been very surprised if we had found something else different from what you find, and we don't. It's the same.
So you know that Karol Dziszkowski is talking about like using these like distances of the eigenstates for multipartite entanglement measures. Are you familiar with that kind of stuff?
No, but it also sounds interesting. No, and then interactions would certainly be interesting, but we haven't also done any calculations on that.
I think that will be very interesting if you know if you can compare with your analytical results with many body interactions. The systems with many body.
I mean, in some sense, we've done actually before this work already. We've done something similar. So if in the context of many body localization, we looked at Drude weights, distributions of Drude weights at the many body transition. And that was, and that's very close. That's actually not so far from these kinds of expressions. So it may actually be interesting to look at these many-body localization transitions in the context of this quantum geometric tensor. That might be another interesting direction to go into.
So any other questions?
Yes.
Sorry, Pragya, you want to ask some more questions? Or?
No, I'm
okay,
through.
okay.
No, I'm through.
Any other question?
I do have a question.
Please.
I'm eating in my own time, but that's totally fine. So
yes, exactly. I'm so comfortable that you are asking the question.
Exactly. So I used all your tricks from the old days, Felix, when I calculated some stuff on delay times. And in delay times, you have a positive definite matrix, basically. So I was wondering if there's any relation between these calculations and maybe the Wishart ensemble.
Yeah, I should know much more about these Wishart things and probably also about the delay.
No, that's I was not.
No, but
anything.
I think there may be relations, and maybe we connect at some point and ask.
I would be very happy.
Discuss it, because I think it sounds interesting.
Yeah, great.
And
Felix,
that I will have to go now because I have another appointment, so I'm not interested. It's not that I'm not interested in your talk. I just have another obligation. I was off.
That's absolutely fine. In contrast, I used this as an excuse to skip out of a meeting, so I was very happy to hear your talk. Exactly. See you.
Okay, so Felix, hello. Felix, very quick remarks. I think Haldane had used this quantum metric, I think, for quantum Hall effect in a very smart way, where I think he was using these coordinates, the guiding center coordinates, which are non-abelian. And I think there is some very nice connection to quantum geometric tensor. And do you have any quick comments? But you have to run, I understand that. So any quick comment on that? You don't connect to those kind of, is there any connection to the work you did?
So in a very obvious question is what happens in situations in which you have not a single eigenstate, but you have a degenerate
Absolutely. Yes, flat bands.
Then you don't
flat bands.
Right, and what's happening there, and I think it's something that I'm interested in, but I don't have anything intelligent to say, so Henning has more time.
Okay, fine, perfect. Okay, thank you very much for the wonderful talk.
Okay,
so
so we
move on.
Great.
Yeah.
Okay, thank you.
Thanks.
So we move on to the next talk. Our next speaker is Professor Henning. He has also very similar interest like the previous speaker. He is a condensed matter physicist who is interested in low-dimensional systems, the dynamics of electrons and phonons in low-dimensional system, the interplay of topology, disorder, and interaction, and dissipations also. He started his career in Japan, in Raking, and then later on he was in Max Planck Institute as a group leader of a young group. And then he moved on to Lancaster University, where he is a professor now. Professor Henning, the stage is yours. Please go ahead.
Thank you. Thank you for the very nice introduction. Thank you for the organizers for inviting me. And I have to thank again Felix for his wonderful talk, even though he might have left us now, because it also serves as a wonderful preparation of what I want to tell you today. I wonder, can you actually see me or only hear me?
No, we can see you and hear you both.
Okay, perfect, because for some reason my own video is not mirrored here. But so I was actually not asked to give a title, so that was very convenient because then I was totally free to select something in a certain way. And what I want to do is to indeed talk about many-body systems, including many-body localized systems, so very complex quantum systems. And I want to take a relatively phenomenological approach to that description. And this is a place where random matrix theory will come in. So random matrix theory is wonderful because you can use it in so many different ways, including doing exact calculations that precisely fit with certain model systems. Or you can use it in order to get phenomenological insights. And in the last talk, actually, both of this became quite clear, including in the discussions where you can do exact calculations, but some of the aspects you can boil down to, say, level repulsion in a very simple setting. Okay, so there is a graph on this first transparency, and we will come back to this. This is about entropies that we want to calculate both from the macroscopic model as well as from the random matrix model, and we want to compare them. But don't worry about the details. So there are many, many curves on this, but we will come back and discuss these in a little while. Okay, so I hope I can flip through this. So what will be the upshot? I already said that for complex quantum systems, random matrix theory provides very useful benchmarks and phenomenological models. So sometimes it's not actually the agreement with random matrix theory, but the deviations from random matrix theory, which are of interest. And of course, we want to talk about many-body systems at the end, but let me, as a sort of a little introduction, start with some observations on a bit more simpler systems, just wave-chaotic systems. That could be classical waves, it could be quantum waves, and these are just obviously a little bit of colorful representations of how these waves might look like. But sometimes they have more or less features related to their spatial distribution. Say it could be a little bit more random over space, or it could be that you find the amplitude focused on certain points, and that we will then call localized. Now, we can use these words like chaotic versus localized, but the terms that we are going to use quite a lot in this talk are ergodic and non-ergodic. And the idea is sort of, if you think about a classical particle moving through space, will it be able to explore all of that space, or will it just explore little parts in the space? Now, still on the single particle level, we can then come up with some benchmarks of what we expect for the ergodic behavior. And maybe the simplest one is to look at the wave functions and say that they're just like a random wave. So how do you do this? You take just lots of waves and make a superposition out of them. And this idea really goes back to Michael Berry, who therefore features again, as he did in the previous talk, but now with one of his other achievements, namely this random wave model. And this is just an illustration, a little bit more recent one. There are lots of illustrations of that kind. For instance, you can look at the nodal wave patterns of a wave in a physical system, which is just somewhere in the interior of a certain billiard, basically an optical resonator perhaps of a certain shape. And then you look in and zoom into the middle and you see these random patterns. And you can compare this with something that you get from just taking random waves and superimposing them. And down to statistical details, this gives you basically the same thing. Now, the next step from the random wave model was to say that for these systems, even though they're actually not disordered, which was maybe a more obvious setting, you can apply random matrix theory. So these systems in the classical limit would behave extremely deterministically, but chaotically perhaps. And the idea is that on the quantum level, you might want to apply random matrix theory. And this turns out so fantastically well for so many different ways to look at these systems. For instance, the spectral properties, the wave functions, and transport are just maybe 3 applications. So for the spectral properties, you would study the eigenvalues of the Hamiltonian, and Felix showed some plots. I will show you some illustrations of this as well. Wave functions are just like these objects here, but the objects which the previous speaker discussed, they are sort of related, of course, in the description, both of this appeared. And transport is if you just contact these systems by leads and maybe pass a current through this. And there are very precise results from random matrix theory that apply very well to these systems. And this actually becomes a whole industry. So you can think about the symmetries of these systems and define lots of symmetry classes as well as universality classes. And this is also the starting point for all the topology, including the band structure topology that many people are interested in. So still in terms of just giving you an easy start into this talk. Just some old graphs from how this all started, because where it started, it was actually with interacting systems. And many people are fully aware of that. So even though the biggest successes for a long time were for non-interacting systems, the cradle of random matrix theory was in interacting systems, namely these complex nuclei, where you can look at resonance spectra and you can ask, for instance, questions of how closely they are spaced. Then you get a histogram, and this one very well fits to expectations from random matrix theory. In particular, expectations coming out of these 2x2 matrices, where you get a simple formula. And now, as I said, it's the departure from random matrix theory, which is just exciting. And in the single particle level, this would be Anderson localization, which I illustrated before in this one-dimensional setting. And here's just another plot in a three-dimensional system with different states localized in different parts of the system. So these are representations of intensities. And if you do that in terms of the level statistics, then you see that you depart. This is just a pretty random model, but it shows nicely these departures from these random metrics, normal, complex, completely random metrics descriptions to this case, which is the Poisson ensemble, where which corresponds essentially to so-called integrable systems or maybe localized systems. And now that actually is data from an interacting system already. So this is somehow coming out of quantum chromodynamics. But at the end, the microscopic origin of these models doesn't really matter. The key thing is that in random matrix theory, there is a lot of universality, and it therefore applies to lots and lots and lots of settings. So now a little bit more modern perspective on these many-body localized systems is to take this notion of ergodicity a little bit more serious. And the way one context in which ergodicity obviously appears with very careful notions is thermodynamics, and that would be based on entropies. Now, there are entropies also in quantum mechanics, and in the very relevant one for us is if you take a quantum system and you cut it into two parts and ask about how strongly these two parts know of each other. So take, for instance, the state that describe the whole system, and then work out these reduced density matrices for one of the two parts. And from this, you can calculate an entropy. That's the von Neumann entropy, or the bipartite entanglement entropy. It is called, yeah?
Can I ask you a question?
Mm-hmm.
Anybody knows what about at this volume law or area law at the transition point, many-body localization point, transition point?
There are some conjectures, like that there is a logarithmic dependence. And that is, for instance, the case in many other transitions. But you asked a very specific question, so that my answer will not mean much to many of the people. But you could, for instance, look also at ground state transitions or transitions in non-interacting fermionic systems. In many cases, you get a logarithm in the length dependence. But before I should explain what the area and the volume law is, actually. So we can come back to this question a little bit later. But yeah, so the difference of behavior that one wants to understand with these entropies is that they sometimes behave like in thermodynamics. And one of the key things of the entropy in thermodynamics is simply that it's an extensive quantity, which means if you make the system larger, the entropy grows proportional to the size of the system, or let's say the volume of the system. In a one-dimensional setting, that would be just the length of the system, but you would have that scaling, and this is what we call the volume law. And just some sort of behavior that you expect from an ergodic system. And then we have other systems which are localized, but now in the sense which we need to understand a little bit better, because that's sort of, it has something to do obviously with spatial features, but maybe not only, because it's also related specifically to the entanglement. So we have other systems which make the system larger and larger, but this entropy saturates. It doesn't grow further at a certain point. And the physics is that the entanglement is then actually quite local. So maybe there's entanglement between parts on the both sides of the interface, but not so much further. And so the other parts of the systems don't really matter. You don't even know in some ways how large the system is if you study this quantity. Now, this is really a feature of the wave functions. And therefore, we definitely move away from the study of spectral statistics to the study of wave functions. And almost all the rest of the talk is about trying to get some phenomenological insights into these wave functions, because they can be terribly complex. And we would like to study them through a bit of a mix of phenomenological ideas and then compare this to microscopic systems, but also develop proper benchmarks from these. Okay, so I wanted to very early give you an idea of what we are talking about. And so I don't tell you what the model here is at this point, but just to give you an idea of what we're talking about, you can start out from a state which is separable, where the parts A and B don't talk to each other, they're not entangled. So the entropy would be 0. And then look at the time evolution. And then generically, you would find that the entropy increases and at some point it saturates. And that might be dependent on some microscopic parameters of your system, but maybe only in the initial dynamics. So maybe you get some sort of universal state here, but sometimes also you end up with different saturation values depending on your on other parameters. And then if you, for instance, do this for different system sizes, then you can get curves like this. So take one of the parameters of your system, look at the average of this saturated value, and then you see that there are some parameter values where your entropy very much depends on your system size, and others where it doesn't. So here we would have something like a volume law. So we make the system larger and the entropy increases. So here are different colors for different values of system size. And we go to larger system sizes here. And there the entropy is already small, so there isn't much entanglement. It tells you that maybe the system is already not much entangled. And then you also see that this piece of entanglement is indeed quite local. It doesn't really depend on the size of the system. Now, as in any good phase transitions, the fluctuations tell you a lot about the transition. So if you look at the variance at the different, basically the values, you see things fluctuate a lot in this time trace here. If you look at these variances, they become large basically at the place where you cross over from this ergodic behavior to this non-ergodic localized behavior. Right. So this is just I wanted to show you this early on so that you have a relatively concrete picture of how you would analyze a system if you're interested in this difference. Now, what is the benchmark? There's a really beautiful benchmark in analogy to the Berry random wave model. There's a beautiful benchmark for the ergodic behavior of these many-body systems. So you look at this reduced density matrices, and then you just, in random matrix theory, always step back and ask, what are the key features of this? Well, this has to be a positive symmetric or at least Hermitian matrix, or at least semi-positive. So it has certain constraints. If you look at its eigenvalues, they are all real and positive. And this is also a matrix which has trace 1. This is just the ordinary normalization condition. But besides this, you could assume that it maybe is pretty much random if you have an ergodic system. And now the way that you can build this is basically you want to have a positive semi-definitive matrix. You can always get this by taking two matrices or a single matrix and multiply it in this way. Essentially, what you do there is something like a singular value decomposition of this matrix here. But there are many different ways to look at this, which actually, if we then take random Gaussian entries, some very natural assumption in random matrix theory for this matrix V, becomes a very specific and well-known ensemble from random matrix theory. Arguably the very first ensemble of random matrix theory, because this person, Wishart, proposed this in the 1920s, I believe. So far before, at the time when we didn't even have the Schrödinger equation. So a long, long time ago. The context was, well, you can think about this as a covariance matrix in any sort of statistical problem, for instance. But in any case, if you then apply this one here, plus the normalization condition, which is not so important if you have a large matrix because the fluctuation in the normalization are very small. If you apply this one to work out this entropy and you calculate the average, you get a very simple result. Namely, you get the logarithm of the Hilbert space dimension with a small correction. So MA and MB are the Hilbert spaces of these two parts, A and B. Now, in a many-body system, say take spins or qubits, then obviously the Hilbert space dimension is just an exponential of 2, the power of 2. And so if you put this in here, then NA would be the number of qubits that you align in a line in region A. So this is really what you would call the system size, how many qubits you have put in here. And the entropy is essentially proportional to this. So that's really a volume law with a very specific dependence here. And actually all these values that we showed up here, they agree precisely with the prediction from this law, which we call Page's law because it was derived by John Page, who was interested in the entropy of a black hole as it happens. So the universality is really immense in these considerations. Now, was there a question?
I think it was by mistake. Sorry.
Okay, no worries.
Yeah,
I'm very happy to
take
questions, and I'm also very happy if I don't get through all of my talk. So please ask questions.
Sure.
So before I showed you an illustration, I should give proper credit to a lot of people, and this is maybe not even. It's just one of the illustrative works, but this many-body localization that we're going to discuss now has been studied for many years. So there is I want to focus basically on two settings in which these deviations from this ergodic behavior really appear. And one is called many-body localization, and the other one has to do with measuring a system from the outside. And it's actually most like 80% will be on the first topic and just a little bit of 20% on the other to just show you how general these effects are. So this is a study of a fermionic system, a one-dimensional fermionic system with some. Oh, this is actually, I think, done on the spin chain. So similar to what I explained above, and we will see Hamiltonians of that form. But here, things are just plotted in terms of a disorder strength. And this is the inset, which is very similar to what I showed you. So if you look at the fermionic system, which is interacting and sufficiently strongly disordered, well, as a function of this disorder strength, as it becomes large enough, you see that all these entropies here become system size independent, while for small values, they approach these predictions from this completely ergodic situation. And again, the variance of the entropy gives you a very good idea of where the transition will happen. So this variance is just large around the point where you cross over from one behavior to the other. Now, I mentioned that these systems are extremely complicated, and one illustration of this is that the most accepted explanation of all of that is very, very theoretical and deep, and arguably not very useful if you want to get direct phenomenological insights. And that's just to say that in these limits, the system becomes an essentially integrable system with some effective conserved quantities, which are all local, but you actually don't quite know which they are. So that gives you some phenomenological understanding, but we don't have a very good idea of many of the key features of these conserved quantities. And so that's basically the motivation for us. So I want to developed some more phenomenological insights into the structure of the wave functions. And this will be really what the rest of the talk is about. Okay. So as a first point, I want to illustrate this difference with the model system, the difference between this ergodic behavior and the localized behavior. And so I show you some data, and then I want to explain this in a phenomenological way. So what this is a chain of spins or quantum bits, the Heisenberg chain with this isotropic coupling and some disorder. And what we do here is we take a finite system of maybe 12 spins and then cut this in different ways, maybe cut it here or here or here or here. And depending on the place that we cut it, we calculate the entropy in the system. So this now depends on the partition point, which is the place where we cut. So as we go to the middle, we get the form of Page's law as I had shown it before, but this can also be done if you cut it not exactly symmetrically. And then this dashed line here gives you the result as a function of the partition point. And now here we have this order, and we can make this, we can take this
can
order.
I ask a question here?
Yep.
Yeah. So I understand that exactly at the middle you get Page's law, but is there a way to write a Hamiltonian which goes even farther and you get something which doesn't have the factor of half? Is it possible to even get rid of the factor of half, or that's
that would be a maximally entangled state. So basically, if you generalize the idea of a Bell state, but this would be of measure zero, so
that's
they would
correct.
probably not appear. So the amazing thing is actually that in an ergodic system, you are very, very close to maximal entanglement.
So there's a very large cluster of states which are just about that place, but that point is, you're saying it's shrinking, the density of states in a sense is shrinking and almost going to zero, right? When you do not
exactly. So a maximally entangled state is of measure zero, but around this, it seems to be a huge volume. So it tells you something about this interesting geometry of entanglement. And so we could, there are states which have an entropy which is even larger, but it can never be much larger. It can only be just a little bit larger. So what we do here is we take this system and we just simply increase the disorder, and we see that this reduces the entropy. And in particular, at some point in the middle here, it doesn't depend on where you partition the system, which is another way to understand that this must be local, because that tells you that the length of the system doesn't matter really. If you cut here or here or here, you get the same result. It means that you don't feel how you have terminated the system. Okay. You can also do this in the same system and simply looking at different ranges of energies. So you can go from the middle of the spectrum where you have lots of states to the edges of the spectrum where you have lots of constraints because you don't have so much extra energy available to explore so much, and you see a similar reduction of the entropy. So there's a transition. Yeah.
One more clarification. This plot is done for eigenstates of the system or no?
This is done for eigenstates.
But with low energy density or higher? These are like close to the ground state, or these are really very high up, very large energy density?
So here each line is for a different percentile. So the ones up here are in the middle of the spectrum, and these ones here are the last 10% closest to the band edges. So you can study it indeed as a function of energy, or you can study it as a function of disorder.
Right. So in the middle of the spectrum has the entropic barrier. So here you go down, on the other side also you go down, and right in the middle there's maximum.
Indeed.
Okay. Thank you.
And you could go even further if you had some additional disorder, but here we start in the place where even in the middle of spectrum we are quite ergodic. So here's one idea of how to get a phenomenological description out of this, and it's actually very simple. You take your system and you make patches out of them. And for each patch, you say that the reduced density matrix should be like an ergodic system. So for each patch, you actually get one of these matrices here. And then you make a product state out of this. So the formula looks horrible. What I say hopefully doesn't sound so horrible. I mean, you need to think carefully what this means in terms of all the indices, but if you look at all the indices, it's a little bit confusing, but what if I put in words, it's actually really simple. So each of these patches is basically like an ergodic system, and then you make a sort of a product state out of this. Well,
yes, could you just remind what is VAB? What is V? Is it a reduced density matrix?
V is really like the factorization of the reduced density matrix. So it's this one here. So you can write the density matrix of each of these little patches. You can look at the reduced density matrix for this, and you say that this must be like an ergodic system, so that you can factorize it in this way, taking V from the random matrix on the appropriate random matrix ensemble. So, and then you combine this into a state which has this property if you do this reduction, but is actually a state which is extended through the whole system. So what you prescribe is sort of a microscopic localization length for the entanglement. Well, if you do this, in a way you're cheating, because then you know that the localization will be just between neighboring patches, and you know that you have an area law. So that's already nice, but then you have too much freedom. You cannot really make any meaningful statements. You can always write something like this, and you can just adjust the size of the patches so that it fits, but you don't really learn too much from that. So therefore, we are going to make the system richer and look at the universality in this description. And so the next step is actually to sum up many of these states. Now, this will generate a much more complicated structure of your states, and I'm not really worried of what it really means. But the way that it is motivated is sort of that if you add many of these states, then you should get to the ergodic limit, because that's the same as Berry's idea, but just done for a many-body system. So there we have now already two parameters: the number of states that we sum up and the size of the patches. And we can even go to compare and think about universality one step further and say, I'm not going to explain this in all detail, but say that these themselves are separable. So that becomes a completely unstructured model. I'm going to tell you again, I don't want to focus on these formulas, but the physical picture, this is as if you have two sides A and B, and all the patches are actually like, they don't talk, they don't know in which they are ordered. They're just like on two sides of an interface. And what this tells you is that you don't quite know, there might be local disorder, but it doesn't need to be exactly between neighboring states. It could be between random pairs of states or random pairs of patches, I should say, okay? And then you can work through your random matrix machinery using some very simple properties of these Gaussian numbers, namely that you can average them very easily, and that on randomly you actually explore the whole space. And then you find the following picture, which is a very nice phenomenological description of the situation, namely that there is only one number which is really important. So there's a huge universality coming out of this. So we have different microscopic parameters in our description, the size of these patches, and how many of these states we add together. And we can do this in two different models, where the minimal size of the system, if you reduce everything, will be two patches talking to each other, or actually all the patches are independent and there's no entanglement. So this is the difference between these two pictures here, where you really have the idea of a one-dimensional chain with the notion of what are neighbors, and something which looks more like a completely unstructured system. But the only difference in there is sort of the minimal size of your effective patches, and that you can construct in this way. And the only thing that matters is actually then this universal number, which is an effective localization length. So this is what comes out of the random matrix theory. So there is a universality in all of these models. So at this point, then you're liberated from saying, I've constructed a model which just which is tailored to a certain description. I have universality, and now I can start to ask questions.
Can I ask you? Sorry,
sure.
Can I ask a question here?
Sure.
So in the previous slide, you had said localization, but was it meant for electrons, or what was the theory? I mean, this is localization for electrons. So who are they for? I mean, or it's a block. There's a sense of localization which you are defining, maybe which I'm missing.
Yeah. So this is this localization in the sense of many-body localization, which you could do for a spin chain, but you can also do it for fermionic systems.
But is there then a sense of Fock space in which you are thinking of localization? Is it the?
I will come back to this question.
Okay.
So
okay,
it's a very good question, because in a fermionic system you have a Fock space, obviously, which has all this anti-symmetry, and for the spins you don't. But it actually doesn't matter too much. That only changes the size of your Hilbert space in most settings. So the number that you stick into here, for spins, this is this number. If you have points that you populate with fermions, because a fermion number is conserved, you get a certain binomial expression for this. But then with that, you, for instance, can again find out what Page's limit would be. Okay, so let me just show you some graphs and tell you that this is actually a very universal description that gives you some new insights, phenomenological insights. And for this, we simply compare our data from all these different variants of the model to the Heisenberg chain. And the first thing is that we can find really good agreement between the dependence of the entropy in the microscopic model, the Heisenberg chain with partitions of different ways, which are the full lines. Which are the data points. So all these data points are from the microscopic model. Then you have dashed lines, and these are coming from the unstructured model. Then you have the unstructured variant of the random matrix model. And then you have solid lines, which come from the structured variant. So the one where we align everything and have an idea of what the one-dimensional system is. And this can be made to fit very, very nicely. And it works actually for both, for all variants of this random matrix ensemble. So this is very universal. There are no big details and differences. And actually, this becomes very beautiful if we do it for a large system. The reason that I show it for a relatively small system is only because for the Heisenberg model, for the microscopic model, the numerics is very difficult for very large systems. But the random matrix model you can actually make extremely large now, because you just write down the wave function with a minimal amount of data in there. So it's very efficient. And then you can extract basically the localization length up to this little factor, this little offset psi naught, which was 2. And you see that this actually really differs by 2 throughout. So in this way, we can define or extract the localization length out of the data. And we see that this localization length actually drops around about to very small values, round about where we expect the transition. So this gives you some phenomenological insights. So on the one side, we have now sort of developed a benchmark for localized behavior. Before, we only had a benchmark for ergodic behavior. Now we have a class of random matrix models with a large degree of universality, which can serve as benchmarks for localized behaviors, including that we can extract a certain number out of this, which doesn't depend on the random matrix description. It's really something that tells you more about something in your system, and you can interpret it as a localization. Now you have this really nice, so that's really the first part. So that's basically done for this in terms of the context of this talk. Let's turn to another question. And this is about indeed asking, maybe a good way to motivate this is to say, okay, that's all fine for spin chains, where we can just write down a separable state for a very localized situation. But if you have fermions, even a separable state has an intricate structure because it needs to be antisymmetric. So you're really working in Fock space. Now, how can we understand the structure of these states in Fock space? So let's take a different Hamiltonian, which is now fermionic. And you have, again, some interactions, which are density-density interactions, just depending on the particle numbers on a certain site. Could have written, this is, again, a chain, so a tight binding model. And then you have random on-site energies. So you have some itinerant electrons in a disordered potential, which are interacting on neighboring sites. And this is actually spinless. And now there is evidence, I can show you a lot of evidence, that in the many-body localized regime, the proper benchmark is not a random state, but is a Slater determinant. That actually sounds terribly boring, but is something that people have not really used, funnily. So, and I give you two ways to look at this. The first one is if we have a Slater determinant, then we can construct this from single particle orbitals. And in order to get an idea of what the single particle orbitals are, we can simply work out the so-called one particle density matrix. So you take, again, an eigenstate of the many-body system, and then you calculate these elements of the so-called one particle density matrix, where the indices are just the sites where the electron can live. And if you diagonalize this, you get eigenstates, which are living in the single particle Hilbert space, and we call them natural orbitals. And we get eigenvalues, and they tell us how much these orbitals are occupied. So these n alphas have nothing to do with these densities. They are the eigenvalues of this matrix here. And so if they are close to 1, then we have a state which is fully occupied. If they're close to 0, then this is an empty state. And in a Slater determinant, you would only find 1s and 0s. So indeed, from this one particle density matrix, you can then reconstruct the Slater determinant. And that works if you have a Slater determinant. And now you can actually work out these occupations, say on average, by averaging over many realizations in a many-body localized system or in an ergodic system. And so let's start out with the ergodic case. There you find that you don't have that structure of a Slater determinant. So you have basically all states, random states occupied with a probability of 1/2, where this is in the case where you have half as many electrons as sites in the system. So this would be your ergodic benchmark. But when we go into the situation where this order is very, very strong and we get localization, then you actually get a step function, basically. So similar to as if you had a Fermi surface with occupied states and unoccupied states, but there is no notion of energy for these single particle orbitals here. But you still get this structure, right? So this tells us that we have another benchmark, namely that we are talking about Slater determinants. And this we can then use in order to get some further insights. So as a next step, we can turn this around. We can take an eigenstate and ask, what are the orbitals which have the best overlap with that eigenstates, assuming that we want to write it as a Slater determinant. So you can think about Slater determinants as a function which depends on the orbitals that you use. And you are free to choose any single particle orbitals. So if you have n electrons, you take n single particle orbitals, and you can do an optimization of your choice until this overlap becomes maximal. This is something that people do in quantum chemistry, and these orbitals that maximize this overlap are called Brooklyn orbitals. And now when you look at states and you just order them by energy in such a many-body localized system, and you look, depending on where you are in energy at this maximal overlap, then this is actually very close to 1. So almost all of the states are very well approximated by a Slater.
Can I make a comment here? Mm-hmm. It just reminds me exactly quantum chemistry in a sense. If you have a good mean field theory, it's telling you that it's tending towards a single Slater determinant, even if it's not in terms of the original degrees of freedom. But there's an emergent Slater determinant which is good.
Yes.
Right?
Yeah.
And it's really quantum chemistry. Yeah, exactly.
Yeah. So this is quantum chemistry, but there's something which is sort of where I will probably conclude. There's something which even the quantum chemists then sweep under the rug, namely, and I think that's something which I found completely surprising, and I didn't find it in any textbook, but quantum chemistries know about it, but they try to ignore it for good reason. If you take a system, even a system where all your eigenstates are Slater determinants, you are not guaranteed to find a single particle basis on which you construct all Slater determinants.
Right. I think what they prescribe to write the many-body wave function as a linear superposition of different Slater determinants, and they try to achieve this. I think this is the best they can do. But probably if it becomes exact mean field, and a mean field becomes exact, then it becomes a single determinant all of a sudden.
Yeah, but even then, if you look at a different state, you don't have, you cannot use the same orbitals, and so this is actually something which occurs in many-body localization. So that's the last thing that I want to show you. So this is it's a very poor representation because 3 dimensions are not enough. But the idea is that there would be projectors onto the single particle space, and they would not all intersect at right angles, the planes of these projectors. But the Slater determinants are nonetheless orthogonal to each other. So the many-body states are orthogonal to each other, but the orbitals are not compatible with each other. And the way that you can quantify this is to say that these projectors onto the single particle orbitals do not commute, because the eigenvalues, the eigenstates basically of these projectors give you the occupied orbitals. And if they don't commute, then we know that we cannot diagonalize them all at the same time. So, well, you can look at the Frobenius norm of these commutators and just look at many-body eigenstates with an index M and an index L and work out on average how big this measure of incompatibility would be. And then you find that it is roughly a half. Don't worry about the details. So a half, that sounds, well, what does it tell us? Well, in order to figure out what this tells us, you of course apply random matrix theory. So what would be this incompatibility if you would take 2 random Slater determinants? Well, in that case, there is this combination of you take one projector and truncate it by another one. And this actually becomes then a unitary matrix, but a truncated one. And so if that would be a full unitary matrix, this is of course just 1. But this is actually a suitably truncated. So you take a truncated block of your unitary matrix and then make this calculation there. And then you can work out in random matrix theory how big this incompatibility should be for 2 random Slater determinants. And for the system sizes that we talk about, this is of the order of 1. So here you see that for a many-body localized system, it is 1/2. So it is almost as bad as, well, it is much closer to what an ergodic system would be doing than a single particle system would be doing. A proper single particle system, you take the single particle states of your non-interacting system and make the Slater determinants out of this. This is, of course, then always compatible, right? I'm sort of running out of time. So these are really the 2 insights. I have something about another transition. I just wanted to explain where the other data comes from, but it's actually not so important. I can cover this in the summary. So my upshot is really that random matrix theory is useful, particularly to also develop benchmarks and phenomenological models. That's actually how random matrix theory started. So people obviously first had a rough idea of how interacting nuclei might behave, Wigner in particular, and then you compare it to data. And then you either find good agreement that tells you that there is something in your random matrix theory which is very representative of your microscopic physical systems, or you find deviations which are just as interesting. And so, for instance, you find deviations from ergodic behavior, and this gives you something about localization. But once you find these deviations, you can try to write down another random matrix approach, which captures these details. And so I really showed you in the context of many-body localized systems 2 ways to look at this. So in particular for maybe spin chains, you can start out from ergodic patches, which would fulfill the benchmark of an ergodic system if studied in isolation. But then you can arrange them into a many-body state, and you can make this random or more and more ergodic or more and more localized by changing a lot of parameters within the random matrix theory. So, and the good thing is that your description does not depend on these details, but it's universal and there's only one number. So that number you can then use in order to get information about physical systems. For instance, you can extract the localization length out of this. And then if you think about fermatic systems, you find that in the many-body localized phase, your proper benchmark are Slater determinants, but Slater determinants which are built sort of out of random orbitals, not compatible orbitals. This actually tells you a lot about this very intriguing idea that these are effectively integrable systems. Because it tells you that, yes, there is some sort of non-interacting descriptions, maybe in terms of quasi-particles, but these quasi-particles must be strongly dressed so that if you look into a certain sector with a certain particle number and work out, and you use one of these dressed quasi-particle operators, you get a completely unrelated Slater determinant out of this. And this is really where I want to end. I just leave with the slide that this is just a small fraction of what you can do in order to look at the transition between ergodic and localized behavior. There are all sorts of properties of the system. Energy density, I already mentioned in some of these plots. You can study this out of equilibrium and superimpose lots of states also in a physical system and look at the time evolution. You can put temporal fluctuations into your Hamiltonian. You can change the range of your interactions. You can monitor the system from the outside. You can increase the strength of the disorder, as we have done. You can, actually the noisy component of interactions drive you to ergodic behavior, but measurements also localize your system, and so does entanglement with environment. And so there's much more to study, but the hope is that there's also a huge degree of universality in these systems that can be captured by random matrix theory. And that's really where I want to end. So I thank you for your attention, and I'm happy to take many more questions.
Thank you very much for the wonderful talk. So now the floor is open for questions. Please unmute yourself and ask.
Yeah, Hiring, can I ask the same question which I started asking in the beginning?
Yes.
And entanglement entropy in the localized regime is area law, and in the delocalized regime it is volume law. So that near the transition at the localization to delocalization transition point, it is expected to be fractal. Okay. Now, because we already know wave function statistics, as you know very well, that shows multifractal behavior from inverse participation ratio and all that. So there seems to be some suggestion that at the transition point, the entanglement entropy should depend on the fraction of the, like instead of area, instead it should be 3/2. 3 of d by 2 actually. Yeah. So I wonder whether anybody has checked it, or anybody thought about it, or anybody has checked it. So do you think what I'm suggesting is correct? That is one question. Second, I will ask you. I'm asking you deliberately. This question is deliberately to drag you. Okay. Mm-hmm. You have been using random matrix again and again. And what exactly do you mean by random matrix? In which context you use? So by random matrix, you mean to say Wigner-Dyson theory, or like its other counterparts, right? You mean to say completely where all matrix elements of the same order. That's what you mean by random matrix, right?
Okay, so let me ask both questions. So the first one is, as far as I know, I know it much more precisely for some other, like the ground state transitions, you actually get a logarithm and not a fraction, not a power, as a system size dependence at the transition point. But I've not personally studied the transition point myself, so I can look into the literature and come back to you and tell you more about it. So that's how I remember it, but I might be wrong. So you might know more about this, and then you know the answer already. So about random matrix theory, I use random matrix theory indeed in many contexts, and certainly not only for ergodic systems. You can study Anderson localization through random matrix theory, and that was actually one of the motivations, because in random matrix, the random matrix description of Anderson localized systems is to take sort of random, say, it can be done in many different ways, random Hamiltonians in these little patches, and then take random, you can think about it as quantum dots, which are coupled by point contacts, or you can use scattering matrices and just make a composition of this. So for instance, you get the DMPK equation, and you get some supersymmetric one-dimensional sigma models in the universal limit out of this. Out of this, I would call random matrix theory. So not only the case where the whole system is described by a Wigner-Dyson Hamiltonian, but in our case, the random matrix theory is indeed with the patches. So random matrix theory always depends on sort of the features which are, you have always some essential features in your system, and you want to make the system random with these constraints. And that could be obviously time reversal symmetry, maybe a chiral symmetry, a charge conjugation symmetry in the superconductor, but it can also be dimensionality. So you can say the random matrix theory of Wigner and Dyson, that's mainly for like an ergodic quantum dot.
Exactly.
But now I have a constraint where my system actually has a one-dimensional structure, and then I get, say, the DMPK equation out of this. So this is sort of trying to translate the logic of DMPK to an interacting system in a way that we can calculate the entanglement entropy.
Do I understand correctly? Do I understand you that you are allowing the sparse random matrices, the matrices where partially random and partially non-random, also you are including as the random matrix, right?
Sure, this is all random matrix theory. Yes.
Because long time ago, I asked this question to Binekar, and Binekar had this he meant random matrix only Wigner-Dyson, and that's what most of the people understand random matrix. When they use the phrase random matrix, they mean Wigner-Dyson. That's why I wanted to have a clear understanding what you mean by random matrix.
Yeah, but Carlo will give that answer. I can't speak for him. I know him very closely, but he has written a review which is called Random Matrix Theory of Transport, and it includes all of that other stuff too, the DMPK equation and localization. It's all in there as well. But the title of his very famous review is Random Matrix Theory
I
of
know
Transport. So and I'm not all books sort of random matrix theory that I know most books will go beyond just the Wigner-Dyson case.
No, but then I'll ask you, I don't want to take time of other people. Then I'll ask you then, in which sense do you mean the deviation from random matrix theory? Because if you're allowing all kind of random matrix theory, which also has partial randomness, non-randomness, then there is no deviation, right? Because then it just means independent random matrices. You have different kind of random matrices applicable to different situations. Then there is no deviation.
So I want to construct meaningful random matrix ensembles, which only include minimal information about the system. So if that means I need to take care of that this is a one-dimensional system, then that's all that I really want to worry about. And therefore, I don't want to have dependence on details. And that's why I emphasize the universality. And I said myself that it's meaningless to just write something in terms of random matrix theory, which is constructed to match what you expect. it only becomes meaningful if you see that this actually doesn't depend on the details that you put into your model and only captures really the phenomenological essence of your system. So that's really the main point of my talk, is to emphasize that point as well. So yeah, you can fine tune, even say you can use all sorts of deformations, say the Poisson kernel, which is still random matrix theory for most people, has already a lot of parameters that you can use to just the details of your random matrix description, for instance.
Okay.
So if you go away from the Haar measure, for instance.
So any other questions? Yeah. Please unmute yourself and ask. I see no other question. Any other questions? No? So then I will ask a question. If nobody.
Thanks. Yeah.
So this, something interesting come to my mind, that what you are saying is, imagine that there's many body localization. Then finally, there's a dressed object which has a well-defined sense of occupancy, and then and the mutual statistics here is assumed to be fermionic. Then it reduces to a Slater determinant. So to contrast it, what comes to my mind is, imagine that you have anions. If I could create anions. Usually anions are localized in the bulk, except for the edge state. But imagine that there's a situation where there's a bulk which is anionic. And then I want to get into the many-body localized phase. Then probably you will have very funny wave functions. Even if there's occupancy, it's a very non-trivial object. And the only context where I can think of asking this question in a sensible way is probably Haldane's exchange, this, what do you call, exclusion statistics, where you can keep a notion of occupancy, but it is still, in a sense, it's more generalized than just a fermion or a boson. You can go somewhere in between. Has there such questions being asked in the context of many-body localizations?
Not that I know of. And I think that could be very worthwhile. I think it's always worthwhile if the systems that you want to study, like the energy systems themselves, are interesting systems. So I wouldn't turn it around and say I make lots of different variants of random matrix theory and want to study it because I can make variants. But if I have an interesting physical setting as the one that you described, then it's certainly worthwhile thinking if there is a description that just captures the essential details of that. Again, personally, I would call that random matrix theory. But
I remember there was some paper by Schouten in the context of CFT where they could create free fermion chains, coupled chains, which host particles which had exclusion statistics, and it has also some strange Cooper pairing. And then that is what came to my mind. And if one does this to somewhere randomizes this, what should I expect if there's a many-body localized phase? What would it look like? Because there's a notion of occupancy, but these are not Slater determinant anymore.
Yeah, so I don't have an answer to this, and I think it's very worthwhile studying it. It also sits strangely between the normal universality classes in terms of symmetries, which is another reason why I think it's study.
It will probably.
If somebody has looked at these models at all from the perspective of random matrix, from many-body localization, not random matrix, it could be people like Frank Pollmann, I think. But I'm happy to discuss this also offline. It's fascinating.
Fine. I'll definitely send you the paper. Yeah, just something which triggered my mind as you emphasized on that sense.
Yeah. Thanks. Perfect.
Okay. Any other question? Otherwise, we'll close the session now. Any other question? Okay. If not, thanks a lot, Henning, for the beautiful talk. And we'll keep in touch.
Yes.
Hope to host you, sometime in physical space, not in cyberspace.
That would be so beautiful. I'm missing that so much, as you can imagine. Yeah. Thanks.
Okay. See you then. Bye-bye.
Okay. See you. Bye-bye.
Okay. So we move on to the next talk now. Our next speaker is Professor N.D. Chavda. Professor Chavda is from University of Baroda, and his interest is in computational physics, quantum physics, theoretical physics, and his expertise span from nonlinear dynamics to quantum chaos and random matrix theory. With this introduction, I would like to request Professor Chavda to take the stage. Hello.
Yeah, thank you for the introduction. Am I audible?
Yes, you're very much audible. Yeah.
Thank you. Thank you. So let me share my screen. First of all, I would like to thank organizers. Now, is it visible?
Yes, it is visible. Yeah, I can see your screen. It's not yet full screen, I guess.
Yeah, just a minute.
Yeah, sure.
Yeah.
Yes.
Okay. Thank you. Thank you. So first of all, I would like to thank organizers for this opportunity. So the title of my presentation is Entanglement in the Two-Body Random Ensembles. In this work, we study bipartite entanglement for finite interacting particle systems, both for fermions and bosons, by employing 1 plus 2 body embedded Gaussian orthogonal ensembles of random matrices. These ensembles are now well established to be paradigmatic models for many body chaos and thermalization in isolated finite quantum systems. These ensembles are more generic compared to spin models, where nearest neighbor interaction one takes. But these models are difficult to deal analytically. So here actually, entanglement is studied computationally. This particular work is carried out in collaboration with Professor Kota and other work. Other collaborators are Professor Potbare, Manan Vyas. She is also giving talk in the next session. Then Harshal Devta and Priyanka Rao. She is a student at MS University, Baroda. So this is the outline of my talk. So I will start with a brief introduction about random matrix theory and a need for embedded two-body interactions. Then I will describe the construction of this embedded two-body random matrix ensembles, both for fermions as well as bosons. And then I will discuss some generic results obtained for these two ensembles. And then I will talk about entanglement in this two-body random ensembles and results about those ensembles, and then finally conclusions. So random matrices were first introduced in the field of mathematics by Wishart in 1928 in the context of multivariate statistics. In physics, they were introduced by Wigner in 1955 to describe the neutron resonance spectra of a compound nucleus. And thereafter, the field of random matrix theory has been developed and applied by Dyson, Mehta, Brody, French, Boigas, Berry, Pandey, and many others. As stated by Wigner, the assumption is that the Hamiltonian which governs the behavior of complicated system is a random symmetric matrix with no special properties except for its symmetric nature. And the interest in random matrix theory is further enhanced when this Boigas, Gionic, and Schmidt conjecture that the RMT should be applicable to spectra of all chaotic systems. So now random matrix theory is not limited to physics and mathematics. So there are various other fields where now random matrix theory is applied. Now, depending upon the global symmetry of this random matrices, Dyson classified these matrices into three categories. One is Gaussian orthogonal ensemble, which describes systems that remains invariant under time reversal and rotation. Other one is Gaussian unitary ensemble, where the system does not possess invariance under time reversal. And third one is Gaussian symplectic ensemble, where the system with half integral spin having invariance under time reversal, but no rotational symmetry. Now, so yeah, this is the definition of GOE. Here, these elements of the Hamiltonian are drawn from Gaussian distribution, having mean 0 and variance 1 for off-diagonal elements and 2 for the diagonal elements. And this matrix H is symmetric. So yeah, for GOE, so we have two variables at each side. And for symplectic ensemble, there are 4 variables at each side. And these basic ensembles can be modified in many different ways. Now, now it is like universally known that this GOE ensembles are multi-body. I mean, classical these random matrices are multi-body, not say a 2-body. So this difference one can obtain in 1-point and 2-point fluctuation. So for GOE, the state density is semicircle, while for 2-body interaction, the density is Gaussian. These are the eigenvalues. Now, if we consider eigenvectors, then for GOE, number of principal component, or it is also called participation ratio. So this, yeah, this is GOE, and while for a 2-body interaction, this is the NPC, and these in 2-body interactions, they are basis dependent. So if we consider like real systems, then real systems, the interaction is, interaction between the particles is at the most 1-body or 2-body. While if we consider this random matrix approach, then it it dominates with M-body interaction, which is unphysical. So so for interacting particle systems, this embedded ensembles were introduced, where 2-body space is the defining space. So here, interaction is defined in 2-particle space for embedded ensembles, and then that interaction is propagated into M-particle space using the direct product structure of the M-body Hamiltonian. So, so this Hamiltonian is GOE or GUE or GSE in 2-particle space, and in M-particle space, it is called embedded ensemble. So these Hamiltonians, which are embedded ensembles, they are also closely related to SYK models, which are in these models were recently introduced in the high energy physics. Now, if we consider GOE version of embedded ensembles, so they are called EGOE2. These ensembles were initially both were analyzed for, fermions as well as for boson systems. Now, as far as like for these two systems, one can have say dilute limit. So dilute limit in the sense, suppose you have m number of fermions distributed in n single particle states. So for fermions, dilute limit is possible, while for bosons, in addition to dilute limit, we have also situation which is called a dense limit. So here, because like so we have like for bosons we have dilute limit as well as dense limit. So in dilute limit, both the fermions as well as bosonic systems behave similarly, but for bosons, this dense limit is unique one. So in the study of interacting bosonic systems, the main focus is on the dense limit. Now, if we consider...
Can I make a comment here?
Yes.
Sorry. You said that this is the same SYK model, which is a Sachdev VA Kitaev model?
Yeah, GG.
Okay, so they got a bit confused. I thought it was initially introduced in a condensed matter context, and it got a bit. I thought maybe there's an analog of it in high energy. And I think recently it came back initially in the context of Majoranas and interacting Majorana from it, right? And and in that's okay. I see. So this is probably the condensed matter version of Majorana where people talked about it. Just curious. I thought maybe it's a similar model. This model is very interesting because it has even crossover ensembles as you tune interactions, and it also depends on how many such spins you take or whatever, how many such electrons you take, you get different ensembles.
So for these SYK models, like it has a block structure, and each block represents this embedded ensembles.
Yeah. Okay. Thanks. Yeah, thank you.
Yeah, so for spinless fermions, suppose if we have n single particle states and m fermions, then the dimensionality of the this system is NCM, and so some of the basis states were shown here, and these are the dimensionality for different n and m values. So one can see as the n and m increases, the dimensionality of the Hamiltonian increases enormously. So these ensembles are also like for a higher values of n and m, they are difficult to deal with computationally. Now, if we consider like a two-body part of this Hamiltonian, so it is defined like in the second quantization form. So these elements are this K, L, V, I, J are the GOE random numbers, and this A dagger and A are the fermion creation and annihilation operators. These matrix elements, they are anti-symmetrized two-body matrix element, and so here these matrix elements are say having mean 0 and variance say 1 for off-diagonal elements, and for diagonal elements the variance is 2. So in two-particle space, these matrix elements are taken as Gaussian random variates, and then so the H matrix is GOE in two-particle space, and then in M-particle space, the H matrix is constructed using the geometry of the matrix. And so many M-particle matrix elements are 0, because of this two-body interaction. And also the matrix elements are linear combination of other two-body elements. So there are basically correlations between M particle elements. So this is about construction of fermionic two-body random ensemble. Similarly, yeah, so these are the non-zero matrix elements for embedded ensemble. Similarly, for bosons, here the B stands for bosons. So for bosons, we have with N single particle states and M bosons, this is the dimensionality of the Hamiltonian, and these are the some of the basis states are shown. And so here also, like, dimensionality increases as one as single particle states and bosons increases. And this is the construction of bosonic two-body ensemble. So yeah, so this is these matrix elements are symmetric in two-particle space, and this this factor square root of 1 plus delta ij takes care of creation or creation of say boson in the same single particle state. Similarly, the other factor, and so here the matrix elements are symmetric, and these are the non-zero matrix elements. Now, now if we consider one body part, if we add one body part into this, then these ensembles are called EGOE 1 plus 2. So this one body part is defined by single particle states. So these single particle states, so so they can be so an energy of the single particle states can be drawn from GOE, or one can take random or fixed. So this is the single particle spectrum, and delta is the average spacing of this single particle spectrum. So basically this EGOE 1 plus 2 is defined by 4 parameters, M, N, lambda, and delta. And if we consider, so basically here we measure lambda in terms of single particle, in terms of average spacing, and one can actually this is the definition of strain function, which is also called local density of states, and these are the definitions for NPC and information entropy. And these NPC information entropy depend on density of states, strain functions, and strain functions. So one can actually obtain smooth forms for these quantities. This is the structure of Hamiltonian for pure GOE. So dimensionality is 252. While here this is this is the Hamiltonian with two-body interaction for fermions. So one can see many of the matrix elements are zero because of two-body nature of the interaction. And the construction was explained about spinless bosons and fermions, but one can also have many other embedded ensembles having, say, spin degree spin as well as parity. So some of the ensembles were analyzed in detail, like this spin ensemble with fermions, then spin ensembles with like bosons and spin. So one can like define. One can include other symmetries, and one can like construct this embedded ensemble with certain symmetry. And this is the book by Professor Kota on this subject. Now these ensembles, as the strength of the interaction lambda increases, they generate 3 chaos markers. So state density is Gaussian, irrespective of lambda, but level fluctuations changes from Poisson to Wigner-Dyson at lambda c. Strain functions initially they are of delta type. Then as the strength of the interaction further increases, they change from Bright-Wigner to Gaussian, and these ensemble also generate a third chaos marker called thermodynamic region, at which the different definitions of temperature and entropies give similar result. So now I will talk about the results of fermionic EGOE 1+2. So this is the lambda C marker. So these markers were verified from various numerical calculations, and also their M and N dependence are obtained. So here one can see as the here this is the example from nuclear physics. So here one can see as the strength of the interaction increases, there is a transition from Poisson to GOE. Similarly, this is about the second chaos marker. So between lambda C and lambda F, the region is called Bright-Wigner domain, and beyond lambda F, where the strain functions, the shape of the strain function is Gaussian. So one can see here as the strength of the interaction increases, strain function changes from Bright-Wigner to Gaussian. Similarly, these are the results for a number of principal components and information entropy, and these are the formulas obtained for EGOE 1+2, where this correlation coefficient, this zeta is the correlation coefficient between diagonal part of the variance of the diagonal part of the Hamiltonian to the total one. This is about the lambda T marker. So here one can see that so here various definitions of entropy are used in this figure. So here one can see for a particular value of lambda, all these definitions give similar results. So the entropies are, the form of the entropy is very close. Similarly, we have obtained these chaos markers for bosonic systems. So for bosons, Yeah, here also one can see for very small value of interaction strength, the nearest neighbor spacing distribution is close to Poisson, and as the strength of two-body interaction increases, it approaches to GOE. We have also try to connect this lambda C with the criterion given by Jacquard and Saplensky's work. So here, basically, lambda C is connected to this B by K, where B is the spectrum span of one body energy within which a particular state of M particle state can be connected by two particle excitation, and K is the average number of such state to which the state can be connected. So basically, B by A gives the inverse of the density of connecting states. So as these like B by K increases, this K by B increases, then there is a chaos. Similarly, we have studied strain functions for bosonic systems, and we all so here also, as the strength of the interaction increases, strain functions change from Bright-Wigner to Gaussian, and we have also studied thermalization in a bosonic system, considering different definitions of temperature. So here, this is the canonical expression using all the eigen energies of the ensemble, and this is canonical expression using occupation number. This is Bose-Einstein distribution, and this is from using state density. So here one can see when the lambda is very small, so strength of the interaction is very small, then these different definitions of temperature give different results. But as the strength of the interaction increases, so at one particular value of lambda, these all definitions give similar result. So that is the way thermalization is defined in terms of temperature. Similarly, one can also obtain thermalization, verify this thermalization using different definitions of entropy. So here we have studied various definitions of entropy, and like in information entropy, entropy from the density of states, and single particle entropy. And we computed this parameter delta S, which gives minimum value when these definitions, I mean different entropies are very close. So that gives a minimum value for this delta S, which defines the thermalization region. And similarly, one can also talk about duality. So here, with 1+2 Hamiltonian, we have two extreme basis states are possible. One is the basis states by defined by H1, and other one is the basis states defined by interaction. So we computed actually this entropy in different bases, H1 and V2, and one can see these from these numerical calculations that for the same value of lambda, both the this strain functions as well as information entropy gives the same result. Okay, so this is about the duality, and this duality marker is very close to the lambda t marker. And we have also computed the m and n dependence of this lambda t. Here we have computed zeta square as a function of two-body interaction strength, and when the variance of or the spreading produced by H1 and V2 they are equal, then the zeta square is like half, so that gives the thermalization point. So that thermalization point we obtain, which is very close to the previous results. Now I will talk about entanglement in these embedded ensembles. So this entanglement, as explained by Einstein, it's a spooky action at a distance, and this is completely like a quantum mechanical phenomenon. And this entanglement between two spatial partitions of a system is greatly appreciated as a useful characterization of quantum correlations in many-body functions. So this entanglement in these embedded ensembles we have computed by partitioning a single particle space. So this single particle space is divided into, so this is part A and part B. This is say it is divided, so total single particle states, so it's a sum of Na and Nb. Similarly, we have m particles, so m1 particles are distributed into in Na, and Mb particles are distributed in Mb. So this is the eigenstate with energy E, and then one can write down density matrix, and the space of bipartite quantum system is given by this equation, where HA is the Hamiltonian of the part A, and HB is the Hamiltonian of part B. If the eigenstate is said to be separable, if one can write down eigen vector by this equation, where this vector AE is residing in the space Hamiltonian space by part A, and similarly BE is the eigen vector residing in the part B. If the equality does not hold, then it is said to be entangled. Now, bipartite entanglement entropy is given by this equation, and so here density matrix. So here density matrix for a given eigenstate is computed, and then the B part. We have traced out this B part. So that gives rho A. And so from the eigenvalues of rho A, one can compute the bipartite entanglement entropy. And for a maximally entangled state, the entanglement entropy is given by log of the minimum dimensionality of the system. from A and B. So these are the results for fermionic ensemble. So here single particle states we have chosen 12 and 6 fermions, and we have taken say Na and Nb by n by 2, and the dimensionality of the system is 294. So one can see that when the lambda is very small, or suppose only one body part is there, when lambda is 0, then basis states itself are eigenstates, and the eigenstates are separable. Now, as soon as lambda is switched on, the basis states begin to spread, and the configuration starts to mix due to a two-body interaction. Hence, the correlations in the density matrix start growing, leading to mixing of subspaces weakly, giving non-zero value of non-zero but low value of entanglement entropy. Now, when the lambda is very small, say around 0.01, so here the wave functions are not chaotic. So their amplitudes of the wave function, there are large fluctuations. So there will be a strong variation in entanglement entropy. Now, as the interaction strength further increases, so more basis states contribute to the eigenstate, leading to higher entanglement entropy. So one can see as the strength of the two-body interaction increases, entanglement entropy increases. The last panel is obtained for two-body interaction only. And this lower panel is the histogram of this entanglement entropy. So one can also see as the strength of the interaction increases, states having larger entanglement entropy, states having larger entropy increases. So these are the results about fermionic system. We have also compared these results with participation ratio, or it is also called NPC. So one can see, here what we have, here one can see that in the tail part, the eigenstates are having low entanglement entropy compared to the bulk region of the spectrum. So this bulk region of the spectrum follow volume law, while the tails follow area law. Similarly, one can also see this entanglement entropy versus participation ratio curve. So here this blue dots are the middle 80% of the using middle 80% of the eigenstates, and this red one are from the tails of the spectrum. So one can see that when the lambda is small, so we have smaller values of entanglement entropy as well as participation ratio. But as the interaction strength increases, these points drift towards the maximum value of the participation ratio as well as entanglement entropy. These straight lines are obtained from the orthogonal distance regression. Similarly, these are the results for bosonic ensemble. So here also the space is divided, single particle space is divided into two equal parts, and entanglement entropy is computed. So here also we get similar results. And these are the entanglement entropy versus participation ratio. So here also one can see that the states having area law, they are in the tail part, while in the bulk region, the states follow volume law. These are the results for Bose-Hubbard model. So these results are also similar to what we have obtained. We have also studied entanglement for interacting spin half chain. This is the Hamiltonian that we have considered. So, this is the disordered chain where one side of the chain where the defect is present. So one side is having a higher magnetic field. So this is the XXJZ Hamiltonian, and so this is the nearest neighbor spins, right? So JXY is the strength of the flip-flop term, while JZ is the Ising interaction strength. And yeah, these are the results. So one can see so we have considered spin chain of having sides 14, where 7 spins are up, and defect site is kept at the center of the chain, and one can see that as the defect strength increases, entanglement entropy increases. But for a sufficiently large strength of interaction, again the entanglement entropy decreases. So here basically, so here one can see localization to delocalization and again localization transition. So as the strength increases, so at for a particular strength of interaction, excitation won't move from one part of the partition from the other partition. So then again we have two parts of the chain, and so again entanglement entropy decreases. Yeah, so this is the conclusion about this work. So here entanglement entropy is studied for spinless fermions and bosonic systems. For a weak interaction strength, the states with low entanglement and low participation ratio appear in the whole part of the spectrum, while for sufficiently large interaction strength, large value in the middle part of the spectrum and small near the tails of the spectrum for both participation ratio as well as entanglement entropy. And we have also found correlations between PR and entanglement entropy, and these results are consistent with Bose-Hubbard models and lattice spin models.
Thank you for the nice talk. So I think the floor is open for questions. Please unmute yourself and ask.
Dr. Chabra, excellent talk.
Yeah, thank you, sir. Thank you for this opportunity.
How are you?
Yeah, fine, sir.
Long time.
Yeah, very long time. I visited in 16 December, ISER Kolkata.
Acha.
Yeah.
Right. You are now in MS University.
Ji, sir, ji.
Yes, already.
Yeah.
I was just informally chatting because we knew each other.
No, please go ahead. Yeah. Please. Yeah, any questions? Please unmute yourself and ask. Then if there are no questions, then maybe.
Yeah, sorry, then let me ask a few questions.
Yeah, please.
There are this, I remember in PRM with Professor Kota, we used to have some time discussions, he used to tell me, there are these exact models of pairing. No? There are some pairing models, which are exactly solvable, right? Are there any sort of random matrix analog of those kind of things?
We have constructed spin ensembles and hello, am I audible?
Yeah.
So we have also constructed spin ensembles, and there we have used pairing interaction.
See, why I'm specifically asking, because as Sorin would certify, this high TC kind of superconductivity, where there is this pairing kind of interaction superconductivity, before it becomes superconductor, there are pairs, but with some but not like superconducting order parameter. So there are pairs are there, but there is pair breaking kind, it's really random kind of thing, with not long coherence length.
Okay.
So therefore, I would imagine in random matrix approach, you will have, if there are pairs which are short distance correlated kind of thing. Okay, those kind of things, are there random matrix analogs?
Yeah, I don't have any idea about this. We have studied pairing interaction, but we haven't
So which pairing interaction? What kind of things you got? What kind of distribution?
Yeah, we study pairing interaction using once we have a spin assigned to these fermions or bosons, then one can easily define pairing. So with pairing interaction, we have studied this what is called how interaction strength, random interaction strength changes the magnetization.
I see. Okay. Yeah. And one more thing I want to ask you. See, for example, when we look at this, Mitra Sengupta, this kind of distribution, where the random matrix is M by N type. So there is lambda mean, lambda max, and that is distribution. Now, suppose if you find like two such domains, when you observe, after removing this correlation, you observe sort of like two domain kind of thing. Are there any kind of random matrix analog which will produce two type of like band kind of thing? Between lambda mean, lambda max is like band lower level, band highest level. Then there's a gap. There's another kind of thing. Are there anything analogs of that?
Yeah, in embedded ensembles, I don't have much idea about.
But it's possible, no? It should not be See, like in convex matter system, we have band system where this energy distribution is there. So that's the kind of picture I'm physically, because I'm analysis of some data is bringing up this kind of pictures. I had sent one email to Professor Kota. Maybe I forward you that later.
Yeah, thank you.
Yeah, okay. Yeah. Thank you, Solomon.
Yeah, okay. So I think I have a question then. So because Professor Panigrahi brought this up, this pairing interaction, when you said, does it mean attractive interaction between pairs? What is a pairing interaction?
Yeah, repulsive.
So why do you call it a pairing interaction if it is repulsive?
Basically, so this let me recollect.
Or maybe conversely speaking, is your ensemble well defined when you make it attractive? I think it will have a connection to superconductivity and can be very interesting.
Attractive in the sense, pairing interaction lowers the energy of the ground state.
But these are repulsive interactions which are lowering the. Maybe you have some exchange energy which you are gaining, but if it is attractive, then this ensemble is. Does it change its character or it remains the same? Or I think that's the curiosity. If it is attractive due to some reason, which you can maybe in the model put by hand, the question is, what kind of ground state do you get with the attractive interaction? Does it support some kind of maybe an incoherent state, but with a strong superconducting instability? If you look at the pair correlation function, probably one can calculate and see what your random matrix is giving. And does it have, it will probably with attractive interaction, it will have like a tendency for sure. But question is, will it stabilize itself, and which kind of ensemble will stabilize it is probably an interesting question.
Okay.
Professor Panigrahi, I think this is what you were asking. This was the curiosity.
Right.
Yeah, okay. Yeah.
In fact, I was asking him, keeping you in mind, but he will take it.
Okay.
You don't want to ask me about the SYK model?
Yeah, did you study that? But I don't know. With one of my master's students, we studied the SYK model, and we saw this was with Professor Pandey from JNU. I think we studied it, and we saw that so in the SYK model, if you look at the standard model which they look at, it has 4 fermion interactions, then 6 fermion, and it's a full series. But you can truncate it at the level of 4 fermion interaction, but completely random, all to all. So there is no range. And then what we did is, this is something we never published. So we essentially switched on 2 particle, in a sense, chemical potential kind of term, two body terms, not four body, 2 body terms, which are essentially solvable, exactly solvable. So once you do that, the degeneracy gets lifted, and what you see is that if it is dominated by the 2 body term, it's Poisson, and then depending on how many particles you take, in this we did it Majorana fermions, I think. Depending on that, you get different crossover ensembles. It crosses over to different ensembles. Your GOE, GSE, GUE. It goes to all 3 of them with a crossover region in between. So it just remained in the master's thesis, and we somehow never put it together. So did you look at that aspect? Did you look at this problem, the SYK model with different perturbations?
No, I haven't studied SYK model.
I see.
Yeah, we have studied this boson and fermion embedded ensembles, and also having various other symmetries like spin, parity.
I see. Okay. Are there any other questions? Please, if there are any questions, please do unmute yourself and ask. Okay. If not, Professor Chavda, we thank you again for the wonderful talk. And with that, I think we close this session now.